Hello and welcome to another edition of Laboratory Software. Might I reintroduce myself again? It's your boy Laz. And today we're going to be checking out Constant Head Permeability testing of soils. I promise I'm not going to get too in depth and whatnot because I know the previous two videos that I've done, I really kind of went into a lot of depth of what the test does and whatnot, but it helps to understand that general explanation. Especially if you kind of enjoy these videos and want to have somewhat of a basic understanding without, spending who knows how long on Google or however much you're willing to spend on Google to figure all this stuff out and whatnot. So, constant head permeability. Really, the word permeability itself should be pretty self-explanatory. The technical term for what this is called is hydraulic conductivity of soils. So it pretty much means how much can water flow through soil and then how much is it affected through that kind of conductivity. So, it really depends on the material types and really, the material type of the soil itself is what's really going to determine what your hydraulic conductivity is going to be. So, for the most part, there's three that people do, and obviously, we're only going to be doing one here, but I'm just going to kind of run through them really quick. So you have what I'm going to be demonstrating tonight, and that's going to be, well, I wouldn't even say demonstrating, but we're going to see how well the software works that comes with this program suite. Constant head permeability. And the idea of a constant head permeability test is that you're really testing sands. So soil that has fines content that's really 10% or less. That's what the specs usually say. Most of the time for engineers, they're testing it on any kind of material that they encounter, but that's usually the go-by rule is this test is really for testing material that has 10% fines or less. So it's really fine to coarse sands is what you're really testing for this with not a lot of silt. Because silts prevent the flow of water. So I might have talked about it a little bit, at least when we covered grain size analysis. So, your particle sizes of your sand vary in different sizes and angularity and whatnot, that depending on what the composition is, I guess is the best word to say, of that, you have to, or not you, but really depending on how that is, that composition can affect the rate of water that can flow through. And, you might be thinking to yourself, well, Laz, why is it important to know how fast water can flow through sand? Well, I mean, obvious reasons, right? I mean, you've seen floods and, you've seen lakes and ponds and dry ponds and retention ponds and things like that. Like these are all critical engineering structures still technically for water mitigation. You want to make sure your water goes to one place without flooding, but also you want to make sure that it can handle it on its own accord in case something else is happening down the stream or the waterway system that's going to process it. So this is why permeability testing is important. It's also the flip side too, where sometimes you don't want a soil to be permeable. Where we see this mostly is landfills. You get that wonderful leachate, which that's the water and chemicals and everything that mix together from waste matter and materials and garbage. And, it's going to collect over time. And the thing is you really don't want that going through the ground, into like, I don't know, let's say the groundwater that people drink from. That's a recipe. It's a recipe for disaster, let me tell you. So sometimes for sometimes it's the flip side where, okay, we don't want it permeable, or we want it permeable enough where only so much water is going to go through, depending on what the intended use and the engineered purpose is going to be for. So that's the overall blanketed thing for why you would do permeability testing on soils. The thing is for Constant Head, like I said, it's really for clean sands. So the idea is that you really want the water to flow through as fast as possible. So let's say you're trying to design what's called a dry pond. And, a dry pond is like a retention pond. So, you have a divot where, the water is going to collect, but the water is going to flow through it faster than it will hold the water, which, all that is an engineering design in itself to determine, do you want a dry pond, do you want a wet pond? Sometimes it depends on what the client wants to, because sometimes they might want a wet pond because it'll add a nice aesthetic to the property and whatnot, kind of like having a small pond or creek or bog, all kinds of different words you can call these things, these water collection systems. I don't know, pick your choice. It's a place where, water is going to be collected. So that's mostly testing for that. The next test that you have is you have something that's called a falling head permeability. And a falling head permeability is really for silts to clays, mostly silty sands, not really too much of clays. You can test it on clays because, if you ever played with clay or messed around with it, if you're making pottery or where if you have Play-Doh or, whatever that may be, you might have noticed that, water doesn't really absorb rapidly or flow through clay as good as sand. If you've gone outside and played in the dirt and made mud pies and things like that, you might have noticed if you poured a bunch of water into sand, while it might stick to the sand granules and you could make things out of it, you need a lot more moisture for it. Unlike if you get clay and you add the same amount of water, let's say 500 milliliters, you'll notice that a lot of it just is, it doesn't absorb. It just kind of stays there in one place. So with a falling head permeability test, that's where you pretty much set it up just like a constant head perm, depending on the size, because you have so many different chambers and devices that you can use to do permeability testing, or if it requires compaction. What in the world am I saying? Compaction or not, which I'll cover more details into that as we check out the program more, because I don't want to keep rambling on. Okay, I know I have a tendency to do that. So for the falling head perm, you'll prep it the exact same way as a constant head perm, which I'm going to cover those details in a little bit. And then, the difference of the test is that, when you connect water to it, or really as you introduce water to it, you're timing how long does it take from the water to filtrate through your sample from one point to another, which, don't get me wrong, the constant head perm is the same thing, but the constant head is a lot more rapid with water, where a constant head perm, you're connecting it to an actual water line itself. Well, really a device that can keep a head. Get it? That's why it's called a constant head. So the head is pretty much the existing pressure that is going to be applied to the sample via gravity. Okay, so that's why that's called a constant head. And in a falling head, you just add water, as much water as you need to, and then you just let gravity just kind of do its thing, and then you time how long it's going to take. I could tell you from my experience, I might have done maybe 3 tops of a falling head perm, and this is like, I don't know, I would say the first 5 years of me working in this industry. And, kind of like what I've explained before, Florida doesn't have a lot of clays and silts. It's not predominant. It's still around on the, in the state, but it's not as predominant as a lot of the northern states and whatnot, where they got clays and silts, and that it's super abundant there. So so we really don't do them. We haven't done them since then. Usually, if anybody wants any kind of material like that tested in that method, we'll usually ship it off to another office to process it. But usually, most of the time, even if it's kind of clay or something, we'll still do a constant head perm, even though it's not really accurate. But I mean, you can still get a flow rate. That's the whole idea of this in the end, is what is your flow rate. So the final one that I've never personally done, I've only seen it done a couple of times, once again within the first 5 years of me working in this industry and whatnot, and that's called a triaxial perm. So that's pretty much clay material, clay, fatty clay. So we're talking over 50% passing your 200 sieve. It's inside a pressure chamber, and it pretty much forces the water to go through the clay. Because don't get me wrong, water, moisture, substances, however you want to say it, will still permeate through the clay. It's not impregnable. So in order to, if you let it naturally do that, it could take years to figure out, okay, well, what's your perm rate? So usually with a triaxial perm, you're using pneumatics, specialized testing equipment and boards, and your samples under pressure, forcing the water to permeate through the sample, so you can determine what's the flow rate, like how fast would it flow. And I could tell you, typically here in Florida and whatnot, if we test anything for clay, for the most part, it's usually landfills. And usually for the landfills, they're usually asking for constant head permeability, because they just want to make sure, hey, generally speaking, if there's moisture or chemicals or whatever on top of this clay layer that will add to this landfill holding area, will this hold the leachate and make sure that it doesn't leach through the clay into the soil, and then obviously you can have an environmental problem really quickly if that were to happen. So typically we'll do constant head perms, and watches the water really doesn't move at all, or slightly moves through it, depending on whatever parameters that they need, or specific type of clays to silt mixtures that they'll use at these job sites. So yeah, I think that's the overall premise here. Hold on here. Okay, sorry. I just had to check my headset here. Okay, yeah, no, I thought I was having an issue there. Anyways, let me take a sip of tea here. Okay, anyways, that's the overall background premise of this. Let's get into the program. Let's get into the meat potatoes. See what this thing can do, because technically, doing a constant head perm, there's quite a few different ways you can do it. I mean, granted, you have a standard test method that you can follow, but usually the devices and stuff that you could use, that's not always the case. So get this bad boy loaded up, and let's see what this actually needs for data and whatnot. That's the thing that I don't know, is what data values is it going to need, because some of the things that we've developed in-house in our lab with Excel spreadsheets, obviously that's always the easiest way to meet your customized needs. A lot of it's kind of foolproof, where depending on which method and or model that we're going to do for constant head perms, can vary greatly. And, I'll cover that a little bit when we really get into the program and see what it can do. I guess before that, do we have, no, okay, not surprised, nobody's on. Okay, so let's open this up. Go to here, go to here, go to here, go to here. Okay, so, all right, let's see, soil test, constant head permeability. All right, so let's see how all this is going to work here. All right, so this is a really, really dumbed down version looking at everything that you need, which really you can kind of pick around whatever method that you're going to use, like what I talked about here. So, all right, so we got description of soil. Let's fill that out. We'll say gray fine sand. Sample number, I don't care. Location. Who cares? Tested by Laz, and, what's today? 12/29/25. Okay, so, all right, so now I'm going to explain a little bit of the testing and the process that we're going to do here. So typically for constant head perms, you have kind of one of two ways on how you can do this. So depending on what's required or what data that they're trying to look for, you can either have what's called no compaction required, which no compaction required usually requires a specialized little slide hammer, and then you do layers depending on the size of your device. And then there's no set amount of layers that you need to have, no set for thickness, no set for amount of blows. And you're just going to do that until your device is completely filled and sealed. And then you can vacuum it. Your other method is, oh, there's a described specimen. I'm sorry, I'm beginning to see how all this is probably going to work now. So your second method is if there's a required compaction. So if there's a required compaction, you have to do what's called a proctor or laboratory compaction characteristics of soils. That's the technical term. And technically, that's going to be the last video that we're going to cover. Will be the proctor test and whatnot. But for this here, so if there is a density requirement for the material to be utilized, so let's say the density requirement is going to be, let's say they want 95% compaction. So obviously you have to have a proctor to go with that. And, with whatever you get for that proctor value, that's what's going to help determine how much you need to compact it. So let's say for this gray fine sand, if there was a compaction requirement and we ran a proctor and we know that our maximum dry density was 105.5 pounds per cubic foot at like 10% moisture, then if somebody says, hey, we need 95% compaction, that would be, let's pull out our handy dandy calculator, if it'll load. There we go. So if we got 105.5 times 0.95, so we would need 100.2% compaction. And that is easier said than done sometimes. Sometimes it depends on the force that you're going to drive into your device itself. It can also depend on the thickness of it, as well as what kind of moisture that you add. I don't want to cover too much into details about proctors because we're that's going to be the last video is Proctor's. So depending on your moisture can also determine where, where it could be. Because, if you get your soil too wet, it could be denser sometimes. But sometimes if it's too cohesive of a soil, then you might want to go lesser on the moisture spectrum. So you might notice with your Proctor curve, okay, so if I need 100 pounds per cubic foot, well, at 7% moisture, or 7.5, or whatever that is, you might notice, okay, well, I can get 100 pounds per cubic foot if I add 7% or 7.5% moisture. Okay, so then you'll add 7.5% moisture, mix up your sand thoroughly or your sample thoroughly. Then you'll put in your perm device, and then you got to make sure that you compact it to get it to a density in order to meet that. Now, granted, with this software here, from how it's looking, I don't think it's going to talk about what density is and whatnot, which totally makes sense. Density's kind of, I don't want to call it an afterthought, but it's definitely not part of the permeability test. The permeability test is to know what is your flow rate of your, the sample that you're testing. So that's the whole idea of this. So that's kind of a side thing that you can do. Kind of like doing a sieve analysis, and I can't remember the law that you can apply to it, but technically when you do your sieve analysis, you can get this D10 value, and you can take that D10 value, add it to this formula that's part of this law, and that will give you a rough estimate of what your permeability rate would be for your material that you're going to test as well, which a lot of our engineers do at times to try to compare what does a lab have as compared to, performing a sieve analysis, with the particles, how it thinks the water would flow through. And, it's at their discretion if they want to pick one or the other or average or whatever. They're the engineer at the end of the day. So, they're the one that signs off on it. All I do is present the data, and then it's up to them to figure it out. So, yeah. So anyways, you do that, you compact it, kind of like what I said. And then I said you're going to apply it to a vacuum. So I wouldn't doubt most people are going to apply it to a vacuum. I think that's the most easiest way. The other way that you can try to compact it, which I've seen in YouTube videos years and years ago. And the thing is, you can submerge your whole perm device in water, and then you just let the force of the water self-compact the sample. Because no matter what, your soil material is going to become wet because we have to flow water through it. So it doesn't necessarily matter if the sand's wet or not. Typically, if there's a no compaction requirement, usually you'll air dry your soil. So kind of like what I stated before, that's an oven that is no greater than 140 degrees Fahrenheit or 60 degrees Celsius, or in front of a fan or something until the catchphrase term, until it's friable under a trowel. So in other words, no sand particles. If you were to put a trowel or metal or anything in there, no sand particles are sticking to whatever you put in the sample itself. That's considered air dry, and or the coin term of friable under a trowel. So, you do all that, and then you're going to hook it up to your head device, and then, you're just going to open up the water, let the water kind of run through, and then you got different methods on how you're going to collect and or time your water. So technically, this is where you're going to run into one of two different perm devices. So you can either have a perm device, which most constant head permeability testing requires that your perm device has manometer ports, at least, well, not at least, it must have two manometer ports. And what the manometer ports do, it literally measures what the head flow is in the sample itself. It's usually in the most center point of your sample itself. And, it has a distance of so far where in between that distance, those ports on the exterior is going to flow water to a manometer that just has, a series of numbers on there. Usually it goes to the 10th. and whatnot. And then, as you take your readings, you're also going to record what your manometer readings are for your first one and second one. And then, with that, that'll tell you what your head is or what the value of H is, which that's your head difference here. Which technically for this, I'm going to try to do it two different ways. So, you know, that's the first way of how I'm explaining it. If you're using that standard perm device, the second kind of device you can get, which is typically used for falling head, but you can also use it for constant head permeability, is it's the exact same device. It's chambered and sealed and everything, but there's no manometer ports. So typically when you use something like that, your head measurement at that point would be the very top of your water. So because your head device is more than likely attached to the wall, and you have a water line connected to it, and it's like I said, the water just pours into a container, and then it has an overflow spout where it can drain into a sink, or it can be self-cycling, however you have your system set up. There's nothing specific about that part. But remember, your water is gravity fed at that point. Once when it goes into your head device, the water that goes through the sample is gravity fed at that point. It doesn't matter if you leave the water on, or if you don't even have a water line connected to it and you just want to keep the head the same by just manually pouring water in there. The thing is remember, understand it's gravity fed. So if you have a specific volume of water, it's going to flow at that specific rate the whole time. So unless you're going to be standing over it with a pitcher of water, if it's flowing really fast, then it kind of sucks doing it that way. That's why most people will actually hook it up to a water line, just so it will maintain it. And then obviously you have your overflow, because you don't want to overflow your head. You want it at a constant pressure that it's going to maintain through gravity, through it being gravity fed. So like I stated, so that there is going to be, well, technically not the top of your head device, but it's going to be the very bottom of your head device, whatever the distance is in centimeters, all the way to the very top of your permeability device, regardless of height or anything. And all of it's recorded in centimeters. Even to get it in feet per day or feet per second, or whatever kind of conversion that you're doing, whether if it's in metric or imperial, everything there is measured in centimeters. So that's the rule of thumb. So that's going to be the second way on how we're going to do it after we try the first way. Technically the most accurate way is the first way, like how I indicated, using a manometer, because it's actually measuring the flow rate of the water inside the sample at the most center point of the sample. So, it gives you the most unbiased, reading for what your actual, head difference is in your specimen. So you do this for a series of tests. I can tell you in the specifications, it doesn't say how many to do. This one has 3 series that you can do. Technically, for our facility, we do 6 as a minimum. So, you can do this 20 times if you want. The difference being, though, with each test that you do, you want your device at a different height every time. So, or if you want to start at the most highest point, or your lowest point, or a middle point, or whatever, you want to have your material at different heights. And the reason for that is, remember, it's gravity fed water. So if it's closer to the water, it might flow faster. It might flow slower. Out of the years of me doing this, personally, and I mean, I've done hundreds, if not close to 1,000 of these tests, on my own. I can tell you, I've never seen any kind of correlation where, usually for any kind of test, there's always a correlation. So for this test, I've never seen a correlation where if it's closer to the head, it'll run or it'll flow faster as compared to further away from the head. I've seen it bounce around all over the place. And granted, I haven't looked at the specification in a while, and who knows, there could be an added note in there currently that might back that reasoning up and whatnot through research and studies. But in my honest opinion, that's likely the reason why they say run multiple tests. And your multiple tests is you're just going to mold it once, do everything that I've described before, but you're just going to do it at different heights. And then you'll get an average, or you'll pick the highest, the lowest. At that point, it's up to what the engineer wants to do. Typically, people will report what your average flow rate is, which that should be our average K, hopefully in the end here. Actually, yeah, it should be, because there's your formula right there to do permeability, at least constant head permeability. So you do that for a series of times. Now, depending on how you're going to do it, the idea is that you're figuring out what is your average flow, and so what your average flow is, and how you get your average flow, you kind of have one of two ways on how you can do this. You can either have a what's called pretty much a beaker. So you're pretty much going to have a known volumed container, which a beaker is the best way to do that because it has graduation marks on it and whatnot. And you can have it where, okay, I want 1,000 milliliters or 500 milliliters or 2,000 milliliters. Like, it needs to fill up this volume every time. It's a matter of how much time did it take to get to that volume, and you report it in seconds for all that. That's why we have our time of collection here in seconds. So all that's reported in seconds, ultimately, for the math and whatnot. So you can either do it that way. The way how we typically do it is, we'll see, and it takes experience, after running multiple tests and whatnot. So we'll just eyeball it. So, obviously when you hook it up and you open everything up, water is going to run through the sample. It's going to run through a pipe, and, usually we have it over a sink and whatnot. So, we're not making a mess in the lab, and we'll see how fast it's flowing through that hose at the bottom of the sample of the device. And then, from there, that's when we'll just kind of eyeball it, and we might say, you know what, let's do 1 minute. We'll do 1 minute tests. And, that pretty much means that, okay, in 1 minute, how much water passed through that material? And that still gets you your average flow. So that's why there's no wrong way. You can do it one way or the other. You're going to get the same results regardless. So, where if you do it in 1 minute and you get like 4,000 milliliters of water, and, let's say 4,000. I mean 400. Let's say 400 milliliters. I mean, you could get 4,000, but that's like testing rock at that point, or an empty chamber. So, let's say you get 400. So, okay, 400 milliliters. That's going to be your average flow. So that's your Q. And obviously, we got to do math and everything, because it's all based on the volume of your device and everything to make all that work, which we're going to input all that stuff in here. And, that's going to be your Q value, and then it's going to do all the math and whatnot. The temperature of water is important because it really determines like what the viscosity of the water is. Kind of like what I've talked about for a lot of the test methods that require temperature taking. It's specific gravity usually. This one's kind of a viscosity thing. But remember, your viscosity, you'll get more viscosity the colder it gets because it's trying to freeze. So in other words, it could be moving slower than what it needs to. Or if it's hotter than usual, then, it could be moving faster than it needs to. But, for this test, you have to get a temperature of your water in degrees Celsius, which, I have all that fun stuff right here. And granted, for the water that you're going to use, it could be regular tap water. It doesn't have to be deionized or anything like that because it's running through the soil sample that has particulates and everything in it. So, and it's running through a device and whatnot to record it. So anyways, that's the whole test that I pretty much explained. That's how you do everything. The only difference is at least we looked at something more than my desktop background on my Windows 10 machine. Okay, so let's start filling this out. So we're going to try filling everything out. We're going to try filling everything out as if we are using a permeability device with manometer ports on it, so we can connect a manometer to it, take readings. So we're going to click on to describe specimen, and here you have to describe your specimen. So for this is going to talk about, okay, what is your sample length in centimeters? So this should be 17.22. Oh yeah, this isn't enter-friendly. Let's see the diameter of our specimen. I do not have that handy. Oh, because it's going to calculate the volume. Crap. All right, so okay, time to think about math. Here we go. All right, so let's see. So usually volume of a cylinder is length times diameter hold on. So okay, so I got the sample length, the diameter. I wonder if it's just two. Let's try. No, it ain't 2 centimeters big. I know, now I got to really think about this because this is data that I actually don't have. I have a volume right here, but I can't fill in the volume. So let me see here. So let's see, length times area. Length times area gets you your volume, but then it depends on what units or what increments that you need. So I'm wondering, length times area. I know, now I'm trying to perform algebra in my head to go backwards here because I have a volume. So technically the volume should be 785.3 centimeters squared. And of course our sample length is 17.22. So you know what I could do? I could just cheat and just start putting values in here. So what if I did... Damn, I'm really trying to think of the diameter in centimeters. I feel like it's 4 inches. I know, I gotta use some conversions here. I know, tonight you get to see me struggle. Neat, right? So inches to centimeters. So let's say it's 10.16 if it's 4 inches. No, I don't think it's 4 inches. But I don't think it's 2. So let's do 8.89. Let's see what 8.89 gets me. Here, 8.89. Oh, wow. Yeah, no, that's really, really, really big. I guess it is smaller. Let's try doing 2 inches then. Man, I just don't think it's 2 inches though, 5.08. Ooh, yeah, no, that's definitely not 2 inches. Or if it's like 2.75, because 349, that's lower, because this should be 785.3. That's the whole thing. I know I'm cheating by doing all this. I could just do math, but it's the issue is I know how to do volume of a cylinder in feet, and I know I could use Google. I guess I could use Google, but hold on. I'm going to play around one more time. So that was 2 inches. That's too small. So let's try 2.75. So we got 6.99. Actually, let's try 7. That's sounding kind of familiar. God damn it. No. I did not want to open Outlook. Okay, yeah, so let's try 7 inches. Or 7 centimeters, not 7 inches. Ooh, that really got me close. 7.50. 7.75. Ooh, 7.70. I mean, it doesn't have to be exact. Let's do 7.65. 7.60. 7.61. Ooh, 62. Yep, that's what it is. 7.62. That's exactly what I need. I know I could have probably just went to Google, right? But I love playing around. Okay, so the length of our specimen, which typically you want a specimen size that can fill your whole chamber. If you can't fill up, or not your chamber, but the device itself that holds your sample, if you can't fill it up all the way, then obviously you're going to measure the difference and whatnot. And if your sample moves around, because it can from vacuum and water settling and whatnot, then you want to put like stopper blocks that are porous, because you don't want to block any of the flow of water, because then you're going to get an accurate reading. Okay, specific gravity of soil solids, we're just going to say 2.65, typical sand. I wonder if this is actually going to calculate density. Mass of specimen, tube with fittings. Mass of tube with fittings with specimen. So I think technically, because I have what the weight of soil is going to be, so I think this, I'm just going to say 0. And this will say 624.38. Yeah, because so technically the way how we do it in our facility is we'll just tear out our perm device, and then we fill it up, and then we'll weigh it again before finishing all the increments and whatnot, so we can get our weight of soil. So that should work technically. All right, cool. So we have all that in there. Okay, so all right, so we got our average flow here. So with this, at least with this test one, I got 342.48. The time collection was 60 seconds. It was 1 minute, but it was 60 seconds. And the temperature of the water is 23 degrees, and the height difference was 70.5. Let's see. Oh, yeah, that's in centimeters per second. Huh. It looks a little off. Interesting. Okay, so here's our next one. So here we got 348.05, 60, 23, and then our height was 72.4.30. I mean, let's just get them in here. And then I'll kind of explain. 341.03, 60 seconds, 23 degrees. And then our height was 74.3. That's not 3. 74.3. That one's 0.29. Interesting. So these are all off by a little bit. Huh. So technically, with the math that I have here with my handy dandy spreadsheet, I'm wondering if it's applying a a different kind of correction factor, because technically the correction factor that we're applying, at least for all of our general data before it gets a final report, is 0.931. And with that, at least with that kind of correction factor, which I'm not seeing that anywhere, everything else makes sense. Huh, actually, it's not dry density of the specimen. W2 minus W1 divided by volume. Oh. Well, that's really weird. So why can't you do... Yeah, why wouldn't it calculate that? So I really need like a value in here. You just can't take 0. Because other than that, it should be that value. So what if I did 1? Oh, good. 625, 38. There we go, because I only added 1 whole extra gram to it. So now it subtracted it and did that. So wow, dry density. Oh yeah, grams per centimeter cubed. I don't know that stuff. Sorry, man. I still use those freedom units. So, now granted for the testing and whatnot, yeah, I mean, I don't know, we'll just have that. And now we got our void ratio, which I'm not going to lie, a lot of people usually don't care about the void ratio. At least for the engineers that we work with, they really don't care. Or they might just calculate it on their own sometimes. Usually all they care about is, hey, what is your perm rates? And, so when you do all this is calculated centimeters per second, but if you needed to get it in feet per day, which is, once again, welcome to America, that's what they're typically looking for. So, I mean, this isn't going to be exact because I already have it kind of pre-calculated here. So even though these would be off with these values here, here, like this is like 80.7 feet per day. This would be like 79.8 feet per day. This would be like 76.2 feet per day with the current volume of the device and everything that makes everything what it is. But me getting back to the correction factor thing that, obviously I've rambled off there. So I don't know, because I mean, granted, this is old. This is an old program. So the thing of a correction factor might have been something that might have come around the early 2000s from temperature in itself. Because a lot of these specifications, when it comes to correction factors from temperature, there's usually a table that you're going to follow. So typically with the water that we run, it usually stays around like 23 degrees Celsius. It's usually, and that's the tap cold here. It's usually 23 degrees Celsius most of the time year round. So, with that, we have a correction factor of 0.931. And I have a feeling these aren't being applied here because technically for test 1, my centimeter per second on my side handout that I'm using here should be 0.0284. So, we have a difference of everything here is off by like almost 0.02-ish, plus or minus. This one's actually a little bit more because this one I got, did I type it in right? Just want to make sure, because, typos can happen. 60.23. Yeah, the head was 74.3. Yeah, 70.5, 72.4, and then 74.3. Yeah, so this is indicating this is 0.029. Or well, it indicates it's 0.029. I mean, obviously you can see if you're watching this, but technically on my handout I got 0.0268, so it could be like point 0.027, at least if you round it to the 10,000s, 10,000, 10 hundreds, thousands, just thousands, 10,000s. Jesus, I can't even count. I know, how educational is this? Fun, right? Okay, so let's kind of switch it up a little bit. So, granted, this is using the device with the manometer ports. So, I was able to figure out the head difference, and usually your head difference is what your two manometer readings are minus one another. So, if I had a reading of, let's say, 70, how I had 70.5. Let's say I had on manometer reading 1, I had 70.5, and then manometer reading 2, I had 50.5. Then technically this would be 20 is what I would put in here. And as you can see, it changed drastically because the formula is basing on what your head is, as you can see from the math down here. So your K, which is your average K value here, 70.5, just to get that back to where it needs to be. So our average K is 0.030, which that's taking these three here to do that, at least with these three tests, even though we did 6 tests. And, everything's all marked here. So, you got your Q times L, so that's your average flow times the length of your specimen divided by the area of your specimen. Actually, hold on a minute. Okay, never mind. Yeah, no, the area is right. Never mind. Because my little handy dandy worksheet I have here in person, can calculate wet density and dry density, but in pounds per cubic foot. So I seen the 45.60, and my dry density was 49.6, depending, but pounds per cubic foot. So that's why I was thinking, wait a minute, is everything off? But no, it's not. That's totally correct. Anyways, the formula's all right here to get it in centimeters per second. Everything here is reported in centimeters per second. So you got your area times your head difference times your time, and that divided by that gets you your K, and that's your hydraulic conductivity. Wow, right? Fun. Okay, so since I have you all here, taking another sip of tea here. Yeah, so since I have you all here right now, and hold on, I'm getting paranoid. Okay, yeah, I just want to make sure it's still recording. I didn't know if my headset was dying or anything. So I haven't had it die on me yet, but I'm prepared to plug it in. Okay, so now we're going to do the other method where there's no manometers. Technically, the head difference is still going to be the same, but the volume of the device is going to change. So let's see here. So this is actually 12.5, and let's see here. That's right. This I had to use a weird factoring thing to make the volume at 245.38. So yeah, because it went over like a 2 times the amount, or it shouldn't be. Your L over D shouldn't be like over a certain height dimension. And unfortunately, like this one was kind of over that. So I had to repurpose the volume so everything could somewhat make sense. So, no, actually, not one. It was 5. 245. Yeah, I mean that's about where it's at. Yeah, 5 centimeters, 245, mass of specimen. We're still going to use everything the same here. So that, except the changes, and now we can see the differences here. And, even with these differences, everything else is pretty well spot on. The thing is just the K factor is definitely different. And it's like I said, my only assumption here is it's only different because it's not applying a correction factor, because we apply a correction factor from the temperature difference and whatnot. Because I think, I think for the correction factor to be at 1, I think it has to be 25 degrees Celsius. I think it's 25 degrees Celsius. I know it's 77 degrees Fahrenheit. That's where you get the specific gravity of value of 1 for water, where you don't have to worry about correction factor for like anything that you're doing. A little bit more background information there that I'm sure nobody cares about, but we'll just include it here because this one is, so this one I got 0.048, 0.047 with rounding, and then this one is 0.045. So, I mean, it's kind of within the ballpark, but it's not accurate. If I had to do software verification, I mean, granted, I'm comparing a spreadsheet to the software that I'm using when all this needs to be hand calculated, which isn't hard to do, honestly. But, I mean, I'm not here to software verify this thing. I'm here to demo and demonstrate and kind of give a little bit of background on what I do and how things work and whatnot. So, all right, there we go. That's constant head permeability right there. And we did it both ways, whether if our device had manometer ports or not, which, I mean, granted, for the example that I had, the head heights were going to be the same because I just made it that way. And, really it was just changing the volume to see how much of a difference we were going to have for our flow rate. So yeah, there we go. That is constant head permeability. All right, let's see. Yeah, no one. I'm not surprised. Okay, just like always. So yeah, there we go. Yeah, so that about wraps up this video here. Hopefully not as long as the previous two. I know those were long, but those really needed explanation on how we get to this point. And permeability is a lot easier to explain. It's straightforward. I mean, it's 20 to 30 steps to do in the lab, but is the easiest 20 to 30 steps that you can do in the lab in order to do this test. This is one of the easiest tests to teach somebody, but just because something's easy doesn't mean that you're going to get it right. You can still mess things up. And trust me, for as long as I've been doing this, I've seen things done so many different forms, shapes, and ways and whatnot that, yeah, I don't know what to say. That could be a whole video in itself and whatnot. So, yeah, hopefully you guys enjoyed this. Obviously I stream these. Usually nobody joins these things. Probably mostly, well, besides the topic or the subject matter, not really, well, being extremely niche for what it is and whatnot. So unless if you're going to school to be a geotechnical engineer or a civil engineer or anything like that, this kind of stuff might peer to your interests and whatnot, just so you have an understanding of, okay, how does this test work and, and whatnot. Really, how does this test work? Because like I said, I'm not showing demos of the actual test going through its process, which I'm pretty sure that would be a lot more entertaining. But, I really kind of need the equipment and kind of the permission to do that, because I don't know if my job's okay with me just recording things is all I'm saying. That would be something I have to talk to them But, I highly doubt that that's going to be a bridge to cross, because I don't think anybody's interested in this anyway. I like doing it. That's why there's a video. You're welcome. You're very welcome, internet. So anyways, hopefully you enjoyed it. Obviously I stream these when I do. There's only going to be one more video left to finish this series up, and then that'd be it. Technically, this is the last video that I'm doing for 2025. I mean, if you weren't paying attention to the date, I mean, obviously it's December 29th. There's like 2 days of December left here. So yeah, no surprise, right? So I don't know when this is going to be posted anyways, but this is technically the last video for 2025. So, I hope you enjoyed this series. If not, you can tell me why. I know I ramble a lot. If you like it, then hey, you can, show your appreciation by letting me know. I know ultimately in the end, I'm still on the fence if I'm still going to host this software that I'm demoing. That's something that I'm ultimately going to figure out by the end of the last video. But anyways, enough of me rambling. I think this video's gone on long enough. I'll catch you guys with the next one. See ya.